In this video, I'm going to talk about the force which is acting on a wire, where the wire has an electric current flowing through it, and this wire is in a magnetic field. And first thing is, force, electric current, and magnetic field are all vectors because they all have directionality. And the equation for determining this is the vector force is equal to the length of the wire that has this current operating, which is inside the magnetic field. It's not the total length of the wire, it's the wire which is operating in the magnetic field. And then there's a cross product, and you please refer to the video on cross products to see what that means. But and for a cross product, the order matters. So the first term is the vector for the electric current. So this has magnitude and direction. And then the second term in the cross product is the magnetic field, which is also a vector, which also has magnitude and direction. And it's easy to remember that, it's helpful for us anyway, that the magnetic field is the letter given for it is beta, so that's B. B is second letter, so that happens second. So it's always the currents first, and then the B term is the second term in the cross product. Because if you confuse them and have the B cross I, then you lose the directionality of this force. So beta is letter B, which is second, and it's the second term in the cross product. Units of this, force for SI units would be newtons, length would be meters, current would be amps, and the SI unit for a magnetic field strength is Tesla. So one could arrange this, so this Tesla is kind of a new unit for us. So one could rearrange this and say that a Tesla is a newton over meter amp. 1 Tesla is 1 newton per meter amp. Where we call an amp is a coulomb per second, which is the rate of charge flow per time. For a non-SI unit, you can tell us it's not even it's not 1,000 or 10,000 or 100,000. It's 10 to the 3, 10 to the 6. It's 10 to the 4. So 1 Tesla is 10,000 Gauss. And these are kind of more units we're familiar with around for Earth in most applications. A Tesla is a very high magnetic field strength, and that's why it's typically Gausses are used as well. But the SI unit is Tesla, which is this. So now go back to the cross product. What does a cross product mean? Well, length is not part of the cross product, it's just a term in it. We know that if I have a long section of, so what makes the force big? If I have a long section of wire that's operating in this magnetic field, you expect that would have more force than a very short section of the wire. So we know that this force is proportional to length. The more length of this wire in there, the more force it has a chance to develop on that wire. You expect the higher the current level, the more amps, also the higher the force. So you expect that to be proportional, and expect also that the magnetic field strength, the higher the magnetic field strength, the more force it would be. So it makes sense that all these three terms, it's proportional to that. But since it's a cross product, the magnitude also depends on the sign of the angle between them. So the magnitude of the length, magnitude of the current, magnitude of the magnetic field, and this is the sign of the included angle between the two. So where theta is the smallest angle it is. So we know that the greatest value that sine of any angle could be is 1. So we know sine because we put 1 and 0. So you always look at the whatever angles they go, find the smallest angle between my two vectors. So if I have a vector going this direction and another vector going this direction, this is my theta. It's my smallest angle between those two vectors as far as determining magnitude. Because this magnitude, the sign will always be a positive number. Where the directionality of the force is determined by the cross product using the right-hand rule of the current across the magnetic field. Now I have 5 example problems here, which we'll work on here to understand what this means. And here I have north pole of a device and the south pole of another part, and between these two parts that we have a magnetic field which is going from the North Pole to the South Pole, And I will say, and for this example, we'll assume this magnetic field has uniform strength across this whole span here. And there's no magnetic field here, magnetic field, but there's between there's uniform magnetic field going in this direction. And I have a wire which is long, but some section of it is through that magnetic field. That length of that section is L, and through there I have a current flowing in this direction. And the question is, what's the direction of the force and what's the magnitude of the force for this case? That's case number one. Case number two, magnetic field here, I don't show the north and south pole, I just show the magnetic field, and the circle with the dot in is showing there's an arrow that's coming out of the screen, because you see the point of the arrow. So the magnetic field is coming out of the board, and it's uniform, and it just operates in this area out here and there. There's no magnetic field. It's just, assume that's just in there. And this time I have a wire which is passing this direction, and the current is flowing in that direction. And the length of that wire, which is in that magnetic field, is here. Here we have a north pole and a south pole here, and I have a magnetic field from the north to the south between those two elements. This time I have a section, the wires coming up like here, and then it has a 90-degree bend to it, and runs here, and it comes down. And just this little section here, which is the straight section running in that direction, is the magnetic field. These sections are not at all in the magnetic field. It just peaks in the magnetic field, and it's operating, and the current is flowing in this direction, and the length of there is L. This one I just show, here's the north pole, there's a south pole, and I have a wire running this direction, and here's the current I going through it. And this one, here's north and the south pole. This time the wire passes through it, comes down and passes through it, so the current is going this direction. So we have 5 cases. What I want you to do is pause the video and solve for the magnitude and the direction. First the direction, and the solve for the magnitude of these 5 cases, and then we'll solve it, and we'll compare answers. So now looking at the answer for the 5 cases. The first one, current flowing through a wire this direction, magnetic field in this direction. So we know that I cross B tells the directionality, and we know that I is this way, B is that way. We know the answer of the force is perpendicular to the plane that contains both these vectors. So drawing it here, B going this way, I is going this way. I really has 2 subcomponents. One of it, subcomponents, the vector of it in I cosine theta, and then in this direction I sine theta. So kind of look at in looking at these 2 components to see the force. So this I sine theta cross this directionality cross B. So the right hand rule, if you recall, put your first term, point your fingers in the direction of the first term, and we're put our palm towards the direction of the second term, and then we roll it like this, and your thumb tells you the direction of the force. So the first term's I, B is B, left second letter B, beta term, the second term. So the I sine theta direction, both fingers palm that direction, so we turn our fingers now into the second term direction, the B direction, the beta term. Thumb points the direction of the force. So there's a force into the board which has the magnitude of the length of this as in the field times the magnitude of the current times the magnitude of the magnetic field times the sine theta term. And you kind of think of, if this is just magnitudes, you can kind of rearrange it. So it's the magnitude of I times the magnitude of beta, and then this L length sine theta term you can kind of think of as that's the length of this wire, which is perpendicular to this magnetic field. So it's this length. It is essentially that term. And then if we look at the second term of this, just to confirm, so during part of the time of this current on this wire, it's traveling this direction, so that's the I cosine theta term, and I cosine theta term cross beta, well, those are in the same direction, and cross product of terms in the same direction have no magnitude, so there's no force from there. So this is the direction of the force in this term is straight into the board, and this is its magnitude. For this case now, B, currents go flowing in this direction along the line. Here's my length of the full current that's in the magnetic field. So we know the magnitude force is going to be the length of that times magnitude of the current times magnitude of the magnetic field, sine of theta. And kind of drawing it out here, we have this is the I and the force. The I term here, the beta term's out here. So you can see that there's 90 degrees angle. So the I and the beta both are on a plane like this, coming out of the board. They're both those vectors. The beta comes out this way, the I is going this way. There's 90 degrees between those, so we know the sine of 90 degrees is 1. So the magnitude becomes just the length times the I times beta times 1. Directionality, use the right hand rule. First term is always I, so point in the direction of I. Palm towards the direction of B. Well, B is out of the board, so palm like this. Okay, so that's why I turn my fingers first in the first direction and then the second direction, and then they stick your thumb out. That gives you the direction of the force. So the force is acting on the wire, acting downward. So that force is being pulled down the board with this magnitude. Third one now, magnetic field going from north to south poles between the parts. The wire's running, comes up and goes this way and it comes down. So there's the two parts, the parts going up and down containing current are not in the magnetic field for this case, so they're not going to make any force. So the only part that's in there is this current term. So I is this direction. So again, the same magnitude. So what's the angle between the I vector and the magnetic field vector? The minimum one. Well, they're in the same. One's pointing this way, one pointing this way, but they're the angle between them is 0, and you can see that the cross product of two terms that have one's in the, if I said typically you say that's the I hat direction, one's in the minus I hat direction. The cross product of that is 0. So this force has 0 magnitude. So the force is just 0. Okay, this term we have magnetic field going from the north to the south. So I didn't draw that, but I draw it. So there's my beta. Here's my I. So by using the right hand rule, I cross beta tells me directionality. First of all, I is this direction, beta is in this direction. So both of those vectors are in the plane of this board. So we know the resultant force has to be coming in or out of the board because it's perpendicular to that, and the sine between those is 90 degrees. So we know it has a magnitude of 1. So right hand rule, point fingers in the direction of the first vector I, palm towards the second term B. So we turn up. So now we can get the force with my thumb extended, which goes into the board. The X denoting the fletching is hitting the arrow. So the force is on that wire, is pushing it farther into the board, and this is its magnitude. Similar problem this one. This time the wire wrapping around, coming back around here. This upper loop of the wire, current's going this direction. So currents in this direction, the magnetic field is in the plane of the board. So both of those are in the plane of the board. So we know the cross product's going to be coming in or out of the board. So let's do it again. So I is this way. Okay, magnetic field it's going from the north to south. So the magnetic field direction is upward. Not show that very well, but yeah. So these arrows are going up. Okay, so first direction, palm is in the direction of the B vector is upward. So beta is up. Okay. So I direction cross the magnetic field this way, palm upward, finger up, put thumb out. So the force 1 is into the board with the sine of theta 1 is 90 degrees, so magnitude 1. So this first force is the length of that wire in the magnetic field times the current in that first loop times that magnetic field into the board. Now let's look at the lower loop. So this part's not in the magnetic field, so there's this part out here gets no force at it, but now I re-enter the magnetic field. So I have a length L2 now in the magnetic field there. Current this direction, magnetic field direction this way, going from the north to the south. So using the right hand rule again, put my fingers in the direction of the I term, the first one. B is second. Okay, B is going upward again. So palm up, so I can turn my fingers towards the B direction. Stick my thumb out. So this force 2 on this second part of the wire wraps around is out of the board. So this is its magnitude is the same magnitude, since I have the same L magnitudes, the same I magnitude, and the same beta magnitude, magnetic field strength. These are the same magnitude values. So there's no net. So the force on the upper loop going in is the exact same as the magnitude of this force 2 on going out. So this wire doesn't want to go doesn't want to have a net force in or out, but it wants to spin, because this one wants to come out and this one wants to go in. So there's a torque. So it wants to spin around. So this is very much like a motor would be, because this wire would want to start to spin from this orientation. What would happen on this last problem if I made the length of the magnetic field longer? Let's say this north part went all the way to here, and the south part would extend all the way to there. Okay, so the magnetic field, let's say it's uniform, and it's going all the way from there to there. So the magnetic field goes beyond this wire, and the current's flowing this way. Does that change the problem at all? Pause the video and think about it. Okay, so here we are. So does it change anything? Well, it does change something. We know that the lengths that are, like for example in this section, the L1 gets longer. Just like the L2 gets longer in this section with this part that's perpendicular. So once again, these forces are in the direction shown, and for this part and that part, the magnitude just goes up because the L term gets longer. So now let's think about that. The wire takes a 90-degree turn here, and I have this I3 term, which is, I1, I2, and I3 are all the same because it's going through the wire. So the real magnitudes, so this is the same magnitude, but this vector is now in this direction. So so I know this one again is making a force, and probably the center of that force would move over to the middle of the wire, and the same thing here. This is out of the board into the board in the middle of the wire, still causing it to twist. But what does this I term going here now, which is flowing, does that make any force? Well, I have I cross B, the current time cross the magnetic field. Now they're in the same plane of this board, but actually one's in the, if I call it the J hat direction, it's the magnetic field, and the current is in the minus J hat direction. So the current is the first term, so that's down. Magnetic field is this upward. There's in the exact same directionality. One's a positive J, one's minus J. So there's no force. So force 3 from this is 0. So there's really no change. This wire doesn't want to go right or left. It just still wants to continue to spin. Two other problems. In this one, we have this area here where the magnetic field, we see the fletching, which means the magnetic field is into the board. In this one, we see the dots, which mean the magnetic field is straight out of the board. And in both cases, I have a wire which comes down, it enters the magnetic field, it has a length L1 here, then it turns 90 degrees and it's going to the right then, of length L2, and then the wire turns and goes up and has length L3, and the current's flowing this way. Same thing in this case. And the question is, what's the directions in the magnetic field acting the wire for this case, and the same thing for this case. So pause the video and solve. The forces for each subsection of the wire is shown in these graphs. So F1 there, F2 this direction, F3 this direction. For this problem, F1 this direction, F2 this direction, F3 this direction. And you can look at, solve these as little subsections because the directionality of the current is changing in these sections. Now, the force is always given by this equation. You can't forget the sine of theta term, where theta is the smallest angle between the current vector direction and the magnetic field vector direction. But you can see for each of these cases, here the current's going this direction and the magnetic field's in the board, so the theta between them is 90 degrees. Same thing here, that direction and that direction, those two vector directions, 90 degrees between those two. Same thing here, magnetic field here, this direction between those two is 90 degrees. So 90 degrees between all those cases. Same thing here, current, magnetic field's out of the board this time, so 90 degrees between these two and that subsection, 90 degrees between these two and that subsection is viewed from the top view. Here, current, magnetic field, current is up, magnetic field is out of the paper, so 90 degrees between those two. So there's, in all of these 6 subsections, the theta is 90 degrees, so sine of 90 degrees becomes 1. So essentially, because they're perpendicular, in all cases the current, the magnetic field, this is a simplification of that equation. Now, so length in each subsection matters, and then the current in that subsection matters, and the current is the same since it's a singular wire running through there, same current. So the current and the magnetic field, like I said, was uniform. So this is the force magnitude in the first subsection, and then all it changes here is the length, and all it changes here is the length. So those are the magnitude of the 3 forces. Directionality, we're going to use our right-hand rule. This fletching here shows the magnetic field is into the board. So that's the second thing we're in, because that's my B, my beta term. So the first thing to think about is the current. So current, put your fingers in the direction of the current. In this first subsection 1, that's the current direction of subsection 1. Magnetic field is into the board. So I put my palm of my hand towards that direction, so I can curl my fingers into the magnetic field direction. Stick up my thumb. So in that first subsection, the force is inward. Second subsection, again, to put all my fingers in the direction of the current, that direction, magnetic field is in this direction, put my palm in there, so I'm going to curl my fingers towards it, stick my thumb up, so in that subsection 2, the force is upward. And here, current is going upward, magnetic field is in, so put my palm toward it, so there's 1 and 2, the second action in the right-hand rule, stick my thumb out, so the force is inward on that subsection 3. So those are the directions of the forces here. In this one, the dot is showing the magnetic field is out of the board. So looking at this first subsection 1, there's my length 1, current's down, magnetic field is out of the board here, so I put my palm in that direction, so I can curl my fingers in that direction. Right-hand rule, stick my thumb out, so my force 1 is there. This time the current's in this direction, put my fingers in this direction. The magnetic field is out of the board, so I put my palm in that direction so I can curl my fingers in that direction. Thumb points in the direction of the force, which is down. So that's the direction of that subsection of force 2. In this subsection of force 3 area, Current is up, magnetic field is out of the board, so I'm going to curl my finger that direction, stick my thumb out, so force 3 is outward this direction. So those are the and then you can, for each of these things, you can sum up the forces to get the net forces acting on there and there from each subsection. And in this one, if L1 and L2, L1 and L3 are the same length, then the magnitude of F1 and F3 are the same, so there's no net force causing this part to move right or left. Same thing here, if L1 and L3 are the same length, these forces are trying to bend the wires out, but the whole assembly doesn't want to go to the right or left, it just wants to go down. In this case, the whole assembly wants to go up.